Hey everybody, welcome back. This is going to be our quick video guide on hand calculating a paired samples t-test, okay? So it's really useful if you follow along with me, so get your calculators and something to write on, and we're going to go slide by slide so that you get the practice you need for the homework, okay? Let's get started. As I've mentioned before, all three of our t-tests, the one sample t-test, the independent samples t-test, and the paired samples t-test, all three have the same three steps. Step one, we calculate the variance for the sample. Step two, we find the standard error. And step three, we calculate the final t-statistic for your specific set of data. So because they have the same three steps, they have the similar three formulas, but each one's formulas look slightly different. For example, to find the variance for a one sample t-test, we have S2 equals the sum of squares over the degrees of freedom. The formula looks almost identical for a paired samples t-test. There's just the subscript d. So it's S subscript d squared is the sum of squares over degrees of freedom. What you should see about all of these is that we just have peppered in the subscript d or MD multiple places. That's because we're going to be calculating the difference between the participants' scores. And so that's why you would be able to pick these three out of like a big pile of formulas and know that they go with our paired samples t-test because they have these D's peppered in. So let's get started with an example. So you're a researcher and you recruit 5 participants to your experiment. You're going to try to teach them an accelerated 30-minute workshop on Microsoft Excel to see if in just 30 minutes you can improve their proficiency skills. So everyone's going to take a proficiency exam as a pretest. Everyone will then attend the same 30-minute workshop, and then they will take that same proficiency exam again. I've already provided you the sum of squares for their scores. As a researcher, you want to know if your workshop is effective in improving Excel skills. So before we get started, let's talk about hypotheses. What would be the hypotheses for this study? The null, H0, would be that there is no difference between the pre and post test scores. Because again, every null hypothesis needs to have some kind of statement of none. So no relationship, no difference. Our H1 here, again, as the researcher, you want to know if it's effective in improving Excel skills. That means this is a directional hypothesis. So our directional hypothesis is the post-test scores will be higher than the pre-test scores. You could also write this as the scores after the workshop will be higher than the scores before. The key here is that this is a directional hypothesis. We've picked a specific direction for our outcome. So if we have a directional hypothesis, is this a one or two-tailed test? It's a one-tailed test. Think of it this way. If you pick a direction, then it's a one-tailed test. If you don't pick a direction, you're going to look in both tails, two-tailed test, okay? So this is a one-tailed test for our hypothesis. Now let's get started on the math. So step one, we need to find the variance. So I'm going to go grab the variance formula from the previous slide. Our formula for the variance is the sum of squares divided by the degrees of freedom. Well, we already know that our sum of squares is 5.20 because it was given to us in the description. So what's our degrees of freedom? The degrees of freedom is one of the formulas that you need to have memorized, and we know that it is n minus 1. Here, we see that we have 5 participants. Thus, our degrees of freedom is going to be 4. So to find the variance, we need to divide 5.2 by 4. Go ahead and do that yourself while I pause. Did you get the right answer? It's 1.30. Let's go to step 2, finding the standard error. Okay, so let's grab our formula from the previous slide. Here we go. Our standard error is the square root of the variance divided by n. So we can go ahead and plug in the variance because we found that in step 1. N is the number of people in the study, and there's 5. So we have everything we need to solve this problem. We have to do what's underneath the square root first. Pause and do that. You should have gotten 0.26. Now square root it. What did you get? Well, you should have gotten this, 0.50990. Notice how I haven't rounded here. I know I've said this before, but it's really critical not to round until you get to the final answer and see what you need to round it to put it in for like a quiz. If you round at every step, you could create so much error that your final answer isn't right. Think of it this way. Every time you round, you make errors. You're either inflating a number or decreasing a number arbitrarily. So it's really critical to use as much of the number as possible in every single step so that your final answer is as close to correct as possible. Now we're going to go on to step 3, which is to calculate the final t-value for our data set. If I grab the formula from a previous slide, we see that to calculate the t-value, t equals md, which stands for mean difference, minus mu d, which would be the difference in the population, over that standard error we just found. So we can go ahead and replace the standard error with the actual value that we found. But what about that numerator? Here's one of those times where things that we do in this class are based on mathematical theory, but this isn't a mathematical theory class. And I'm aware that many of you don't necessarily care about learning the mathematical theory. So this formula here, the mean difference, that's something we're going to have to calculate. But the mu difference, for us, that's always going to default to 0. If it defaults to 0, why is it in the formula? It's in the formula because, again, for mathematical theory, there could be a time when a difference in scores is known about a population, and thus the known population difference would be put in there to take that into account when you are looking at your mean difference. However, this is a psychology class, not a pure math class. And when we think about using statistics in psychology, it is very, very, very rare that we would ever know that. So for us in psychology, especially intro undergraduate psychology, that number will always default to 0. But we're left with the mean difference, so there's still part of this numerator we don't know. To find that out, we need the actual score for our participants. Well, so here they are. You can see our 5 participants. Their numbers are in that first column on the left. Their scores on the pre-test are in the middle column, and their scores on the post-test are in the final column. So if it's called mean difference, then I clearly need to calculate the difference, which is subtraction, and then an average of all of the differences. That's basically what that formula says, is the summation of D, the summation of the differences between scores, divided by how many scores there are, or how many people. So the easiest thing to do is to add another column here, which is going to be our differences. To work through this, we would take our post-test minus our pre-test. And for that first one, it would be 10 minus 10, which is 0. For the second one, it would be 9 minus 7. It's really important that if you have a pre-post-test design, the post-test is always first in your calculations. That's because the signs matter. Just like with a correlation, we can interpret our t-values, whether or not they are positive or negative, as to whether or not the post-test scores were higher, positive t-value, or negative, meaning that the t-value is negative, their scores on the post-test were lower. So if it is a pre-post-test design, the post-test has to come first. If it's the other kind of design, the kind of test 1, test 2, like everybody in the study does one thing, takes a measure, and then does something else and takes a measure, that doesn't necessarily matter which one comes first. Here, where it's time dependent, pre and post test, the post test has to come first. So 9 minus 7 is 2. Pause and do the rest of these. Did you get the right answers? You should have found 0, 2, 1, 2, 3. So again, if the way we calculate the mean difference, these are the differences, So we have to add them all up and come up with an average. So you would add 0 plus 2 plus 1 plus 2 plus 3, and then you would divide by 5 because that's how many people there are. Pause and come up with your answer. Is this the number you got? Again, if you add those things together, you should have gotten 8. 8 divided by 5, because there's 5 people, 5 pairs of scores, means that our mean difference is 1.60. Now we're ready to go back to that formula. So we can substitute in 1.60 for our mean difference. Again, mu difference defaults to 0, and then the denominator is that standard error we already found. So go ahead and pause again and come up with your answer. For our t statistic for this data set, you should have gotten 3.13787. And again, that's a positive number. It's a positive number because we did our difference scores correctly. And as you can see, all of our post-test numbers are higher than our pre-test numbers, which means our differences for each participant are also positive. If our differences are positive, then our mean difference is positive. If our mean difference is positive, then our t statistic is positive. And again, that would tell us that our post-test scores are higher. But just like with a one samples t-test and an independent samples t-test, just because you have a t observed value, a t statistic for your specific data set, doesn't mean that you can answer the question, is this statistically significantly different? To do that, we need the t-chart. So here's our accessible t-chart. Remember, if I don't tell you that we are using the alpha at 0.01, it means that we are using the 0.05. We already talked about that the hypothesis for this is about improvement, which is a directional hypothesis, which means we are looking for the proportion in a one-tailed test at the 0.05 level, which means we're going to use the second column here, the column that is the first one with t-values in it. Our first column, of course, is the degrees of freedom. Remember that there were 5 people in the study, which means our degrees of freedom is 4. So our t statistic for comparison is going to be 2.132. If we have a t critical of 2.132, that means that if we look at our t distribution, which resembles the normal curve, the boundary that marks the difference between the critical region in the tails and the rest of the distribution would be at 2.132. Our observed t statistic is 3 point something. So it really doesn't matter what the rest of the numbers are because it's over 3. That means that it's larger than our t critical. Since our t observed is larger than our t critical, it means it is in fact in that extreme positive tail. That means it is statistically significant. So when we go to interpret that, we can say that yes, we can support our alternative hypothesis and reject our null. The workshop is effective in improving the participants' Excel skills. And of course, if this was real life, that would go on how I advertise that workshop to make that money, honey. So, anywho, I hope this was helpful, and I'll see you online.